Hi guys, welcome to Math TV with Professor V. In this video, we're going to be working on homework exercises for the section on finding areas between curves. This is part 1. This topic comes from chapter 6.1 in James Stewart Calculus, 8th edition. It can either be covered in Calc 1 or Calc 2 depending on what school you're going to. So let's get started. The directions are as follows. Sketch the region enclosed by the given curves and then decide whether to integrate with respect to x or y. Draw a typical approximating rectangle and label its height and width, then find the area of the region. So actually the first couple examples will already give you the graph of the region, and then after that we'll have to do them by hand. So this one's a little easier. So example 1, notice here we have y equals cube root of x on top in pink, and then y equals 1 over x below. Here's the region. It's bounded by those two curves. They intersect at 1, 1. They found that for us. And then they're cutting it off. We're adding also the vertical line x equals 8 to bound the region. Okay. So if you're trying to figure out whether it makes more sense to integrate with respect to x or y, you want to look at the region and say, is it bounded on the top and bottom, or is it bounded on the right and left? And at first you might think, well, it looks like both, but no, not really. So here, this curve, cube root of x, bounds the entire region on the top, right? Like you could draw a typical rectangle anywhere, and the top is always determined by cube root of x, and the bottom is by 1 over x. That's bounding it below. If you try to go the other way, okay, look at the problem that you run into. So yeah, x equals 8 is bounding here on the right, and then this curve, cube root of x, is bounding on the left. We would have to rearrange it though to be in terms of y. But then what happens right here at 1, 1? It switches, and then you still have x equals 8, and then now 1 over x is bounding on the left. So you would have to split and set up two integrals because the curve switches. So I don't like that, right? Who wants to do that? So instead, we're going to integrate with respect to x. And let me go back and put that cute little rectangle that I had in the beginning because that one was great. Here's a typical rectangle. Okay, I'll draw it all the way up here. It doesn't have to be super perfect. So height of that rectangle is going to be top minus bottom. So top curve is cube root of x minus bottom curve is 1 over x. And then the width is delta x, which when we integrate is going to be dx, right? Okay, easy enough. Since we're going to integrate with respect to x, let's write that down to remind ourselves. Integrate with respect to x. And what should the limits of integration be? Well, the region starts at x equals 1 and ends at x equals 8. So those are going to be our limits of integration. So area is going to equal definite integral from 1 to 8. And we're going to have cube root of x minus 1 over x dx. Okay? Good. Now just crank it out. So I like to rewrite everything in integral friendly format, meaning instead of cube root of x, I'm going to rewrite that as x to the 1/3. 1 over x, no, I'm not going to write it as x to the negative first because remember, we don't integrate that using our power rule. We have a special rule to integrate 1 over x. Do you remember what it is? Think about it, think about it. Okay, so to anti-differentiate x to the 1/3, you add 1 to the exponent, so that's going to become x to the 4/3. And then you divide by the new exponent. You divide by 4/3. But a cleaner way of thinking of that is you're just going to multiply by the reciprocal, right, of that new exponent. So reciprocal of 4/3 is 3/4 minus, and then antiderivative of 1 over x. This one you just have to memorize. It's natural log of the absolute value of x. And yes, put those absolute value bars on there as long as there's a variable inside, okay? As long as it's still x. And we're going to evaluate this from 1 to 8 now. Good? How you guys doing? Hanging in there? Okay, so now I'm going to substitute in my limits of integration. So I'm going to have 3/4 times 8 to the 4/3 minus ln. Now, when I put in 8 for x, that's already positive, so I don't have to write the absolute value anymore. Ln of 8 minus, this is 3/4 times 1 to the 4/3 minus ln of 1. Okay, don't get your calculator. Don't even think about it. We can do this. So 3/4. How do you figure out 8 to the 4/3? Okay, I'll show you right now. I'll do it off to the side once. 8 to the 4/3, you take the cube root of 8, and then you raise that to the 4th. That's how you do it. Okay, so cube root of 8 is 2, and then 2 to the 4th, that's 16. Oh, that's all it was? That was 16 in disguise? Yes. Minus ln of 8 minus 1 raised to any power is just 1, so that's 3/4. And then ln of 1 is 0. Okay, so here we've got 16 times 3, that's 48 over 4, minus 3 over 4, so that'll be 45 over 4, minus ln of 8. That's it. That's your exact answer. Okay, those terms can't be combined. Nobody wants a decimal. Give your answers exact unless your instructor or the book indicates otherwise. This is how we want it. Beautiful. Okay, let's do another one. Again, this one, the graph is given, okay? So look at the region. Is it bounded above and below by a curve on the top and a curve on the bottom, or on the right and left by a curve on the right and a curve on the left? Look at what makes more sense. It's bounded on the right and left. Yes, can you see it? You know what another dead giveaway is? They already wrote the equations in terms of y. X equals, so you're already set up to integrate with respect to y. So here's my rectangle. This is going to be the height. That's going to be the width. So the height is always right minus left, bigger minus smaller, right? Things get larger in this direction in terms of x. So what's bounding the curve on the right? E to the y, minus on the left, it's y squared minus 2. That's the height. And then the width is delta y, which becomes dy in our integral. And then what should the limits of integration be? Well, they're already kind of like helping me out. We're bounding it by y equals -1, and then above y equals +1. Okay. So area equals integral -1 to 1. Height I have here, e to the y. I'm going to distribute the negative, okay? Minus y squared plus 2 dy. And then we can just integrate term by term now. So this is going to be antiderivative of e to the y is just e to the y. Negative y squared. So add 1 to the exponent, divide by 3. This is going to be -1/3 y cubed plus 2y. Yeah? You're okay? Good. Evaluated from -1 to 1. Now let's evaluate this at our limits of integration. So we're going to have e to the first minus 1/3 times 1 cubed plus 2 times 1 minus, this is going to be e to the negative first minus 1/3 times -1 cubed is going to be -1 plus 2 times -1. Woo! Okay, so let's see what's going on here. We've got e minus 1/3 plus 2 minus e to the negative first. This is going to be plus 1/3. But then we have another minus sign here, so that's minus 1/3. And then same thing here. This is minus 2, but then I have another negative, so that's actually going to be plus 2. Okay, so we can add these all up. -1/3 and -1/3, that's -2/3 plus 4. -2/3 plus 4. 4 is 12/3. 12/3 minus 2/3, that's 10/3. Okay, and then you have e minus e to the negative first plus 10/3. Could leave it like that, or e minus 1 over e plus 10/3. I like the last one. Let's box that one. Looks nice. Okay? Try to only use your calculator when absolutely necessary. Your brain is a muscle, and just like any other muscle you exercise, it's not just a muscle, but you know what I mean. I think of it that way. And just like any other muscle you exercise, you know, if you're just lazy and you don't work it out, it's going to get all noodly and mushy and not be strong. But your brain, like, work it out, use it as much as possible, and only use the calculator when necessary so you don't have a mushy noodle brain. All right. Oh, now we got to graph them by hand. Okay. I'm just going to number them how they are in the book. 5. So we have y equals e to the x. Y equals x squared minus 1. And then x equals -1, x equals 1. So sometimes we're going to have to find the intersection. In this case, we won't. Because they gave me e to the x. We know what that looks like. X squared minus 1, that's a parabola. They also gave me these two vertical lines, which are going to bound the region. So we don't have to worry about finding an intersection, okay? And the intersection occurs outside of -1 and 1 anyways. So let's just get a rough sketch going. I think the hardest thing for students is graphing, which is sad because it's so necessary, you know? How to fix that? I don't know. Review pre-calc. E to the x. Do you know what it looks like roughly? So e to the 0 is 1. Yes. It's an ugly looking 3. Hold on. E to the 0 is 1. And then let's just go. We only have to go to -1 and 1, right? They're already telling me these two vertical lines bound the region also. Boop. Boop. E to the negative first is about 0.4. Not that it matters for the graph, but you know, let's put that in there. So nice. And then e to the first e is about 2.7. So this is e to the x here. Ooh, nice. And then x squared minus 1, that's a parabola opening upwards that's been shifted down 1 unit. If you found the x-intercepts, they would be at plus or minus 1. So here and here. So here's the parabola. Okay, and they were so nice to bound the region by -1 and 1. Why? Because it would be hard to solve and find the intersection. You'd probably just use technology, okay? Can't really do it by hand. And then here is the region whose area we're trying to find. Okay, so you guys tell me, is this region bounded above and below or on the left and right? Above and below, you say, yeah? Okay, I hope that's what you said. So we're going to integrate with respect to x. Let's draw our typical rectangle. Let me do a different color. Here it is. Okay, so how do we find the height of the rectangle? Top minus bottom. You guys, all of these bounded areas, they should not be negative, okay? When you find an area under one curve in reference to the x-axis, it could be positive or negative, right? It's signed area, but these are between curves. It's not going to be negative. If you get a negative, you did it wrong. So height is going to be top minus bottom. E to the x. Minus x squared minus 1. And then the width is going to be delta x, which is the same as dx when we integrate. So we're integrating with respect to x. All right, here we go. So area equals integral. We're going to go from -1 to 1 because they bounded it with the vertical lines for us that way. And then top minus bottom is going to be e to the x minus x squared plus 1 dx. Are you guys okay? I distributed that negative. Oh, good. This is so similar to the last integral that we did. Antiderivative of e to the x, e to the x. Antiderivative of x squared, -1/3 here, x cubed plus x from -1 to 1. Okay, and then we're going to have e to the first minus 1/3 plus 1 minus, this is going to be e to the negative first. You guys, let's see if we can do this in our head. Negative 1 cubed is negative 1. And then times negative 1/3, this is going to be plus 1/3 and then minus 1. Ooh, okay. And then we have e to the first. This is going to be plus 2/3 minus e to the negative first. This is a negative 2/3, but then I have another negative here, so plus another 2/3. And our final answer is going to be e minus 1 over e plus 4/3. Okay, looks good. Super similar to the previous one. We just had to graph this guy on our own. Okay, moving on. Next one, number 7. We have here y equals x minus 2 squared and y equals x. So x minus 2 squared, that's a parabola shifted 2 units to the right, opening upward. Y equals x, we know that's just a line. Slope is 1, goes through the origin. In this case, they didn't give us any other lines or curves to bound the region, so we do need to find the intersection. Don't even think about doing the problem without this crucial first step. Like, you can't even graph without finding the intersection. You can't graph properly. So let's just set x minus 2 squared equal to x. I'm going to multiply out x minus 2 squared. So it's going to be x squared minus 4x plus 4, oops, equals x. I got too excited. Set this to 0, so x squared minus 5x plus 4 is 0. That factors, thank goodness. X minus 4, x minus 1 is 0. So they're going to intersect when x is 4 or x is 1. And I do want the y coordinates, you know, for my graph. And easy place to get them is just by plugging into y equals x. So if y equals x, then that means they intersect at 4, 4. And 1, 1. So let's draw our graph. And the intersection is so important because it'll help you figure out what your limits of integration need to be, as well as setting up a proper graph of the region so you can identify which curve is on the top, bottom, right, or left, and how the region is bounded, okay? So looks like I can just stay in quadrant 1, 2, 3, 4, 5. That's where all the action's happening. 1, 2, 3, 4, 5. And the graphs intersect at 4, 4. 4, 4 should be here. And 1, 1. Okay, well, the line is easy to draw. That's y equals x right there. The parabola, if you need to review parabolas, then just go to my YouTube channel under the pre-calc playlist. The vertex is at 2, 0, and it opens upward. So that means the parabola is sitting here. And you don't need really much else. Like if they're going to intersect at, oh, that's not 2, 0. Forgive me, that was 3, 0. Here's 2, 0. They're going to intersect at 1, 1 and 4, 4. Just draw something that makes sense. Ooh, that looks good. So this is y equals x minus 2 squared. And then where's the region? It's right here. Okay. So how shall we integrate with respect to x or y? Is it bounded on the top and bottom or right and left? Top and bottom, yes. Y equals x is always on top. X minus 2 squared is always on the bottom. If you said right and left, you know why you'd have a problem? Because you have a right half and a left half to the parabola. You would have to solve for the equation in terms of y, and then you would split it into 2 right here. No, not fun. Okay, so we're going to integrate with respect to x. And then here's our rectangle. Okay. Height, top minus bottom. So x minus 2 squared. And then the width is going to be delta x, which is dx. Okay, very good. So now let's set up our integral. A area equals, what should the limits of integration be? They should be in terms of x. Where does the region start and where does it stop in terms of x values? It starts here where x is 1 and it stops here where x is 4. So we'll integrate from 1 to 4. X minus 2 squared dx. Okay. Now, if you're a little new at integration, I want to show you why you definitely don't want to multiply this out. No. And you don't even really need to do a u substitution. Okay. I'm going to show you little tips that are going to help you save time in the long run. So just consider, this doesn't need to be part of your homework, but if you feel like this is a new idea for you, then write it down. If you had the integral, okay, of x minus 2 squared dx, I'm going to show you why you don't need to do u sub by first doing a u sub. If I let u equal x minus 2, du would be what? dx. Okay. Then my new integral, instead of x minus 2 squared, is just going to be u squared du. You anti-differentiate, so this is going to be 1/3 u cubed plus c. And then you go back, replace u with x minus 2. Yeah? Okay. But look, really, we didn't need to do all of that because since du was equal to dx, the only thing that happened is that -2, when you took the derivative, it went to 0 anyways, right? So couldn't you have just in your head imagined this is just a u, and then come here. Now it's cubed and you divide by 3, right? Why are we allowed to do that? Because the coefficient on this x was still just 1. So that's why du was equal to dx. And really the u substitution didn't help us a whole lot, right? It didn't like clean up the integral. Maybe it just helped you visualize the steps a little bit better, but hopefully you can start doing them in your head. Let's try. And definitely you don't want to multiply this out, FOIL it out. Then you'd have more terms to integrate, more places that you'd have to evaluate the limits of integration, more places to make mistakes, okay? So don't do that either. All right, so let's try now. Antiderivative of x is going to be 1/2 x squared. And then minus, and I'm going to pretend I didn't even do that u sub. I'm not going to look at it. I go, oh, if I did the u sub, du would be dx. So I'm just going to keep x minus 2 together, right? Like it's its own little family hanging out. And then add 1 to the exponent, divide by that exponent. So 1/3, just x minus 2 stays together like that, cubed, 1 to 4. See? How nice. Okay, now plug in your limits of integration. So we have 1/2 times 4 squared minus 1/3. 4 minus 2 is 2 cubed minus, and then we have 1/2 times 1 squared minus 1/3 times 1 minus 2, that's -1 cubed, is still -1. Okay, so let's see what's going on here. 1/2 times 16, that's 8, minus 2 cubed, that's 8. So 8 minus 8/3. Minus, this is 1/2. And then this is going to be a positive 1/3, but then there's a minus sign, so minus 1/3. Okay. So this is -8/3, -1/3. That gives us -9/3, which is -3. So I have 8 minus 3 minus 1/2. 5 minus 1/2 is 10/2 minus 1/2, so this is 9/2. And we're done. How are you doing? Okay. It is only with perfect practice that you can improve. Let's move on. Next one. Number 9. Here's the two curves. y equals 1 over x, and y equals 1 over x squared, and they gave us also x equals 2. So let's go ahead, let's find the intersection. Do you know what 1 over x looks like? It's like that, more or less. That's super sloppy. And then 1 over x squared is just here, okay? So we're gonna be in the first quadrant because this guy is basically, you know, here and here. There's no intersection happening anywhere other than quadrant 1. Okay, so let's see what's gonna happen. It's gonna happen in quadrant 1. 1 over x equals 1 over x squared. You can cross multiply or just take the reciprocal of both sides of the equation. It's the same thing. So x equals x squared. Don't divide by a variable. I hope you didn't even think about it. We're going to set it to 0. Factor out an x. And we get x equals 0 or x equals 1. The x equals 0 is not in the domain. It would make both curves undefined. It's actually where there's a vertical asymptote. So throw that out. They're going to intersect at x equals 1 and nowhere else. So one intersection point wouldn't close or make a bounded region, which is why they gave us this additional vertical line at x equals 2. Okay, so at x equals 1, both curves are equal to 1, right? Can you imagine that just by plugging in a 1 here? So they're going to intersect at 1, 1. And then at 2, 1 over x, that's going to be 1/2, and then 1 over x squared is going to be 1/4. So I'm just going to draw, a very tiny bit of the first quadrant. Oh, yeah. So x-axis, y-axis, we're only going to go up to 1. Here's 1/2. Here's 1/4. And then I'm not going to scale the x-axis the same. I don't want to. It's my graph, my world. All right, so 1, 1, they intersect. And then at 2, 1 over x is equal to 1/2. So I'll say that was too aggressive. Hold on. This is 1 over x. And then 1 over x squared is going to be 1/4 right here. The graph is important so you know which one's above, which one's below. Here's x equals 2. So here's our region. Do you like it? It looks nice, huh? Okay. Okay. So should we integrate with respect to x or y? X for sure. Can you tell yet? Here's the rectangle. Let's find the height and width. So height is going to be top minus bottom. 1 over x minus 1 over x squared. Width, delta x, which is dx. Okay, looks good. Let's set up our integral. Limits of integration have to be in terms of x. Regions bounded from x equals 1 to x equals 2. So let's go 1 to 2. Top minus bottom, we have it height 1 over x minus 1 over x squared, and then dx. Okay, you can rewrite it if you need to. 1 over x, we know the antiderivative is going to be ln absolute value of x, but for 1 over x squared, I'm going to write it as x to the negative second, okay? Because we're going to use our power rule. So antiderivative of 1 over x, ln absolute value of x, minus x to the negative second. So add 1 to the exponent. Now it's going to be x to the negative first, and then divide by the new exponent, divide by -1. Well, that's just going to cancel with the minus sign in the front and make it positive. So I'm just going to do that here so it looks clean. Evaluated from 1 to 2. Okay, good. Keep the absolute value on the x, but then now I'm going to drop it because now I'm substituting in 2. So ln of 2 plus 2 to the negative first, you guys, that's 1/2. Minus ln of 1 plus 1. ln of 1, that's 0. And then we have ln of 2 plus a half minus 1. So that's going to be ln of 2 minus 1/2. And we're done. Voila. Are they getting easier? The more you do, if they get repetitive and you're like, I feel so bored, that's good. Then you're getting the hang of it. Okay, couple more. Let's look at number 11. So we have x equals 1 minus y squared, and then x equals y squared minus 1. So these are parabolas that are opening to the right and left. How do I know? It's because we have y squared instead of x squared. Okay, so 1 minus y squared, it's being shifted and opening in the negative direction. So it's going to look like this. It's shifted to the right. And then y squared minus 1 is shifted to the left, and it's opening in the positive direction. So they're going to intersect. Let's find where. So in this case, it's easier just setting the two curves equal to each other and solving for y. Let me add y squared to both sides and add 1 to both sides. So then I have 2 equals 2y squared, which is the same as y squared equals 1. So they're going to intersect at y equals plus or minus 1. Ooh, so if y is positive 1, both x values are going to be 0. And if y is negative 1, same thing. Okay, so that's where they intersect, 0, 1, and 0, negative 1. So let's get a graph going. 0, 1, 0, negative 1. I'm trying to think how to scale, you know. So we'll do all 4 quadrants, but we just don't need to go outside of 0, 1, really. Okay. So always think before you start graphing. I see students sometimes, they put the x and y axis and they start like making all these tick marks out to 10, but you don't need it. Where's all the action happening? Right here. 1, 1, negative 1, negative 1. So they intersect at 0, 1, and 0, negative 1. And then if you want to find the vertex, you could, or I could just look at it here. Like if y is 0, like let me show you. If y is 0 on this parabola, x is 1, yeah? So if y is 0, x is 1, that's here, and this one's opening in the negative direction. How do I know? Because the coefficient on y squared is negative. Probably haven't thought about these kinds of parabolas since pre-calc days. And then the other one, same thing. If y is 0, x is negative 1. So this one's opening the other way. How do I know it's opening in the positive direction? Because the coefficient on y squared is positive. This is why you can't forget any of your math, because it just all builds, you know? Can you see the region? I'm sorry, it looks a little lumpy, but it's not bad. It's in here. Okay. So I definitely don't want to do top minus bottom. Why do I say that? Because first of all, if you do top minus bottom, you have to integrate with respect to x. So I'd have to rearrange the equations for the parabolas and solve for y in terms of x, and you'd have nasty square roots. And it's pretty clear one curve is always on the right, one curve is always on the left. Can you see it? So draw your rectangle this way. Which curve is always on the right? This one, opening in the negative direction. That's 1 minus y squared. Which one's always on the left? This one, y squared minus 1. So you see how the region's bounded on the right by 1 minus y squared, bounded on the left by y squared minus 1. Beautiful. So the height, we're going to do right minus left. Always think bigger minus smaller. If you switch it, then your answer is going to come out negative. Right minus left, that's going to be 1 minus y squared minus y squared minus 1. That's the height. And then the width is delta y, which is dy. Good. Okay, so let's set up our integral. The limits of integration have to be in terms of y, -1 to 1. That's what bounds the region. So we're ready to roll. So area equals integral from -1 to 1. Right minus left, we have 1 minus y squared minus y squared plus 1 dy. Don't start integrating. I know it's exciting. Combine your like terms first, always. So -1 to 1, we have 2 minus 2y squared dy. Okay, good. Antiderivative of 2, 2y. Antiderivative of 2y squared, 2/3 y cubed. Good. From -1 to 1. And then let's substitute in the limits of integration. So we'll have 2 times 1 minus 2/3 minus, what's this going to be? -2 plus 2/3. So this is 4 minus 4/3. So that's 12/3 minus 4/3, which is 8/3. And I want to point out to you guys something. Another way we could have done this integral, since the region is symmetric with respect to the x-axis here, we could have instead integrated from 0 to 1 instead of -1 to 1 and then doubled the region. And that would have been an easier computation. Okay? But you have to be careful when you apply that the region truly is symmetric and that the limits of integration match up and everything, but just so you keep an eye out for when that pops up later. I don't want you to be alarmed. So speaking of that shortcut, I'll do one more example for this part 1 video, and we'll go ahead and try that out. So this is number 13, and here's the curves. Y equals 12 minus x squared, and y equals x squared minus 6. So that's all they gave us. This is a parabola, the first one, opening downward that's been shifted up, and this parabola here is opening upward. So let's go ahead and figure out where they intersect. So 12 minus x squared equals x squared minus 6. It's super similar to the last one, right? Let's add x squared and add 6 to both sides. So 18 equals 2x squared. Divide by 2. So x equals plus or minus 3. And so if x is positive 3, I'm just going to plug it in here to figure out the y coordinate. 3 squared, that's 9. So 3, 3. And then if I had -3 for x, I'd get the same thing. So that's where they intersect. 3, 3 and -3, 3. And then this parabola, the vertex is going to be at 0, 12, right? So it's shifted up quite a lot. And this vertex is at 0, -6. So the y-axis, I'm going to have to scale out pretty far. X-axis, not so much. So let's see what makes sense. I'm gonna count by 2s, you know, why kill ourselves with 12 little tick marks? Doesn't sound fun to me. X, Y will go 2, 4, 6, 8, 10, 12, 2, 4, 6, okay. And then 2, 4, 6. Here's 3. That was an interesting point for us, right? 2, 4, 6. There's -3. Okay. So let's see. Parabola 1 goes through 0, 12. And it intersects the other one at 3, 3. Let me mark where 3 is on the y-axis, right there. So here's 3, 3. And -3, 3. And the x-intercepts are going to be plus or minus rad 12, yeah? I'm just going to figure out what that is approximately. Rad 12, 3.5-ish. Oh, so like there. You don't need that, but I like to just kind of have a somewhat accurate graph. Okay. And then the other parabola, x squared minus 6, I'm going to intersect at the same place. This one's opening upwards here and here, and then its x-intercepts are at plus or minus rad 6, so that's like 2.4-ish. The intercepts aren't important for the intersection or to do the integral or any of that, but I just feel awful crossing an axis and not knowing exactly where that's happening, okay? So obviously it keeps going like this. So does this guy. But the region that we're interested in is right here. Okay, and hopefully by now you can see it's bounded above and below. So we're going to integrate with respect to x. It's bounded above by 12 minus x squared, and it's bounded below by x squared minus 6. So the height, we're going to do top minus bottom, 12 minus x squared minus x squared minus 6. Let's just clean this up now. That's 18 minus 2x squared, right? And then the width is delta x, which is dx. Okay, let's double it because it's symmetric with respect to the y-axis. Can you see? So for our limits of integration, you could go from -3 to 3, or you could double it and go from 0 to 2. Let me show you. Ooh, this is going to be fun. So area you could do from -3 to 3, 18 minus 2x squared dx. And then if you want to compute it this way, it's going to be easier. Double it, go from 0 to 3, 18 minus 2x squared dx, like that. Okay, and then, let's see, don't you love having 0 as a lower limit? 2, just keep the 2 outside. Antiderivative of 18 is 18x minus, this is going to be 2/3 x cubed from 0 to 3. And then let's substitute in 3 for x. So 2 times, this is 18 times 3, that's 54, minus 2/3 times 3 cubed is 27, minus 0. Okay, let's see here. 2/3 times 27, this cancels. This is now a 9, right? So it's 54 minus 18. What's 54 minus 18? It's 36, right? So 2 times 36, this is 72. Okay, so that concludes part 1. Part 2 will come shortly. Or check out the poll that I have. If you want to tell me which section you're working on right now in your summer class, then I'll record that next. All right. Thanks, guys, for your support. Make sure if you need any review or help, go to my main YouTube channel. I have all the video lectures there for pre-calc, Calc 1, Calc 2, Calc 3, Trig, you name it. I'm here to help you.